Ready, rock?
Yeah, let's do it.
Cool. So, hey, I'm John. I'm a software engineer in Antithesis, where we provide deterministic simulation testing as a service.
So, and I'm Brian, and you'd think to have a testing company, you need pretty good tests, right? But it's not easy to do that. So we're here to talk about, testing ourselves, why that was hard, why we decided to do it anyway. But before we get into that, let's take it back. Why do we care about testing so much in the first place, right? Like, what's the matter with bad testing? Lots of companies do just fine. They make it years with weak tests or almost no testing at all. And I'm not going to bore you guys talking about prod bugs because everybody here has seen that, right? The alarms go off, the system goes down, users get angry, like whatever. We all know that stuff. What I want to focus on is what it does to you in the time in between when nothing's on fire. So I come from a little bit of a DevOps background. I have been first in line to get paged at a few different companies. And what I find is that changes the way that I think about everything. I get defensive. I get paranoid. Somebody comes and proposes a cool new feature that will make our product great, that our users will love. And my first thought is, wait, what's that going to break? Your choices when you don't trust your tests are to become defensive or to become reckless and say, whatever, it'll be fine, our users will forgive us. Or, in the worst case, you become both of those things, where it's like, I'm going to break stuff, but you better not. It doesn't have to be like that, right? There is another choice. So what does good testing actually look like? Anybody here have good tests? There we go. This is the only room in the world where I actually believe people who say that. And you guys who have good tests know that living in that is just like a completely different environment. It's like going into battle with a force field, right? Like, I still have to try my best. I still have to try to get things right. But I'm not constantly looking over my shoulder. I'm not waiting for the other shoe to drop all the time. And it changes the way that our engineering team behaves. We're more confident. We're more ambitious. We're more likely to go after the root cause of some problem instead of slapping a Band-Aid on. And for some of the more ambitious people here who have taken on deterministic simulation testing for themselves, what they know is that it brings some of the crazy ideas, stuff that seems impossible, just barely into reach. So what does good testing look like?
So, like Brian just mentioned, we think deterministic simulation testing, or DST for short, is like the gold standard of testing. We care about that so much, we made our own alliance just to prove it. And this helps you in a few ways. It helps test as much of your application as possible, get your app into really weird situations you didn't think of, and makes it easy to reproduce any issue that we find. So there's a few main parts of that. First up is determinism. The key idea there is that if you give a program the same input, you're going to get the same output every time. And having this property means that any bug you find is always perfectly reproducible every time. And one thing to note is that you only need the determinism when you're testing. If your production app isn't deterministic, it's not a big deal. It'd be great if it was, but we only care about the testing. And that leads to the next main part, is the simulation. Because most software isn't deterministic. So you need to make your own simulated version of all that to force it into be deterministic. So things like networking libraries, file I/O, system calls, or any third-party service you use, you're going to have to make a fake simulated version just to have your tests behave in a deterministic manner.
Right. The outside world isn't deterministic, so if your tests need to be, you have to get the outside world away.
Yeah, exactly. And the last key piece there is some randomness. So in traditional testing, humans are writing tests for the things they thought to write tests for. But the bugs are lying in the areas you didn't think to write your test for. And since the system is behaving deterministically, if you don't add any sort of controlled randomness to it, you're just going to be running the same test over and over and over again. And usually in deterministic simulation testing, people really care about faults. So they use the randomness to randomly turn on faults to kill the connection, slow packets, do anything like that to make their system behave in really, really weird ways and hopefully pull up all those bugs that you want to catch. So deterministic simulation seems pretty cool. So how do you actually use this thing?
Right. And we've got some experts on that in the room. And so, you guys can say, you want to get DST working, all you have to do is write your program from scratch alongside a simulator that handles all of the edge cases and mocks out the entire rest of the universe. Super easy. There's a reason when you look up DST and see who's using it, the people that you see are a little bit fanatical. There are people who really think that bugs are existential. There are people who take every single one as seriously as possible and want to hunt them down because it changes the entire way you architect your system to build it for simulation testing. But that's not how most companies work, right? That's not how most development works. Most of the time, you have a cool idea, you're curious if people will like it, you have no idea. You bang out a prototype, you show it to some people, they give you some feedback, you turn it around, you play around, you iterate, and then, one day you've got this thing out in front of some users and the feedback comes back, wait, this is awesome, sign me up. And then what do you do, right? Then you're in a hard place because you can either stop where you are, lose the hype, give up your momentum, start over somewhere that you really think you can support this thing, you can test it well, you can maintain it, or you do the normal thing, you push on ahead, you say, yeah, it'll be fine, we can figure this out later. And you're now dragging along some code that, maybe you wrote in a hurry, maybe it was some interesting ideas, and you really have no idea how to support it. What we need is a third choice, a way to take good testing and wrap it around the software that you already have, something that'll give you that breathing room to do the important refactor or build out the next new feature, where you can see that you're not making things worse, even though you're working with something that maybe wasn't the strongest thing you could have built in the first place. So at Antithesis, that's what we're building.
So Antithesis gives you the benefits of deterministic simulation testing to all of the non-insane people who haven't done it already. We take your containers, run them inside our platform, and then give you a report of any issues we found. And the main coolest piece of it is our hypervisor. So we built a hypervisor that will make any software running on top of it behave deterministically. We don't need to chase down making this tech stack, this framework, this language behave deterministically. We just made the whole computer deterministic, so we get all of that for free. And I won't go into too much detail of how it works, but our colleague Alex has done his own talk and one blog post going into it. But at the core, we emulate any CPU instruction that behaves non-deterministically to make it fit into our deterministic model. And then any random input the system will request, we have to give it to it from the outside. And we also don't allow any sort of external network calls because we want your system to be a pure function of the input we give to it. So that way, if we relied on external network calls, that would break determinism as we reproduce something. As we replayed an input, how do we know that network call is going to give us the same exact response? And since, again, it's a normal computer, we can just run Linux on this thing. We can run your containers, since that's probably how you're deploying your software anyways. And the other benefit there is that we can use that to inject our faults into your containers. We can kill them, drop the connections, slow packets. Anything you think of that you want to test your system, we can make happen just using normal container technology. And when you take a step back and think about it for a second, the hypervisor makes your system a pure function. The only input that it needs is what we provide. So instead of thinking of execution of your program as a single line, we think of it as a giant multiverse, a tree where it branches with every input we send to it. Those inputs could be things for randomness or commands we inject at arbitrary moments. And instead of running the same test over and over and over again, we can explore this multiverse and notice when interesting things happen and focus on those parts to hopefully find interesting bugs. And then any node or state we see, we can just replay the same inputs and get back to it. And this is a very similar concept to traditional fuzzers, where you give random input to a program and see if it crashes. And we named our software explorer, the next part of this, our fuzzer because of that. So we have this giant multiverse of every possible execution path your system could take. Some parts of those have bugs, some parts don't, and we need a way to explore. You could just do pure randomness, just give random input arbitrarily and see what happens, but this tree is infinite. It's every possible state your program could get into, so we need a better way to guide our exploration. And the simplest way is through code coverage. You could instrument your code, and then anytime we go down a new code path, our fuzzer will notice that and spend some energy seeing if it leads to anything interesting. So for example, if we turned on a new fault and that triggered some error handling code, we would notice that and then go down there and try everything possible to see if some new code gets hit. We could also look for specific log lines. So if you care that a certain log is important to you, we could tell our fuzzer and give it to focus on that as well. And we can do a lot of crazy arbitrary features that are really, really cool that, again, we can't go into too much detail here, but our CEO, Will, gave a really cool talk last year on how we developed our fuzzer by playing NES games, which is a great watch I really, really recommend. So Antithesis obviously seems really complicated. So how did we test this thing?
Right. So, it would be really nice to say, we started building this thing, and the first thing we did was put it in Antithesis and see how it went. But, when I joined the company in 2018, Antithesis literally didn't exist. Like, we didn't have a name yet. So we had to figure out other ways to test our stuff. And we went through a lot of different strategies along the way. So when unit tests, right? When people hear that I work at Antithesis, one of the first things they say is like, you must hate unit tests, right? Unit tests are fine. Unit tests have a place. They're great for when you have a contract you're keeping, when you have an API that deviations from it are bugs. But as soon as you pull back from that, they transform really quickly into change detection tests that, as soon as you see them read in your report, your first thought is, oh, the test is wrong, I need to update it. And you don't even notice the bugs they do catch. As soon as possible, we started testing end-to-end. End-to-end tests are great at exercising functionality. If you write them well, they'll catch pretty much everything that your customers will catch, and hopefully they'll do it sooner. On the other hand, they have a lot of the same problems as finding bugs in prod, right? They're still flaky, they're still often slow, some things will break some nights and not other nights. And when you do find a bug, you don't have any good guide toward where to look in your code for it or how to go about fixing it. Our code is full of assertions. We love assertions. They supercharge every other form of testing we do, and they even turn production into a little bit of a test, right? If something is going to break, we want it to break as clearly, as loudly, and as directly as possible. We want a guide to fixing things. The problem with assertions, traditional assertions, is that if an assertion doesn't fail, you don't know whether that's because you're always going through in the happy path or whether you're not getting there at all. It's easy enough to write code that you think is passing your assertion and you have that in your mental model, but it turns out, I got an if statement wrong somewhere above and I'm never even running through it. This one's a little bit subtle, but it has saved our lives. So the hypervisor obviously has to be deterministic, right? That is what we're offering people. We're saying we can make systems deterministic. But everything else, because the hypervisor is deterministic, can sort of do what it wants. And so our fuzzer didn't have to be deterministic. It could just, every time you start it up, feed some new set of inputs. We decided to make it deterministic anyway because determinism is a super sensitive test property for changes that you didn't realize you were making, right? So as this thing got big and complicated and refactors started getting scary, it was possible for us to say, hey, we changed a bunch of code, but it was definitely a pure refactor because when we run it side by side with the old thing, every step executes exactly the same way. But of course, that's one bit of information. And if you are actually changing something, it's totally useless. Now if I add a new feature, if I change how something works, that determinism is gone. It doesn't tell me anything. Like I'm back to square one. And finally, we found that we couldn't quite wait for ourselves. And so, we took advantage of the determinism we built in the fuzzer and actually built a little single-purpose DST, right? We mocked out the hypervisor, started feeding in random inputs, and we basically had a fuzzer. This was great. This was my first test of really good, first taste of really good testing. It felt like even some of our gnarly old code, I could go in and change something, and I would know if I messed it up. It was super cool, but it was just this one pocket of our system. And at one point we did it again somewhere else. But it only covers the areas that you specifically build it for, and not only is it missing the entire rest of the system, it's also missing the places where the things that it is covering meet. And lots of bugs love hiding in those places. So going through and doing all of these other tests informed us a lot and made us think of what we wanted to be adding to our product that wasn't just what you get out of DST, but the things that we were really hungry for as people writing and fixing bugs. So what else do we want? We want stable, high-level properties. I want to be able to describe my system and know that something is being held, not at the function level, but at the system level. We want to be able to tell that we're exercising interesting code. I want to know that the tricky assertions are actually showing up in our test runs. And we want it to be easy to debug, right? When we do actually find something, when a test comes back red, we want to have as easy a time as possible tracking down where in our code that happened and what we can do to make it better.
So that's what we built next. So we wanted to utilize all of these interesting properties of the multiverse. So we built properties to help describe bugs. We use our strong invariance of knowing exact execution order to make our properties even stronger. And we utilize determinism to make debugging a crazy experience. So first up is properties. Since we're randomly exploring the system, we need to know when we hit a bug. We can do everything in your system, but if we don't know something was a bug, what was the point of us doing it? So the simplest kind of assertions we can make is like a property. And this is similar to a normal assertion you would write in your code. And this is just asserting that no container has a seg fault at all. And we have a lot of these for different kinds of languages, crashes, all that kind of stuff. And these are exactly like your traditional assertions you're writing in your code. But since we have all of these different possible execution branches, we can do a sometimes assertion. Something that only happens every now and then. And a great example of this is sometimes a leader election happens. You can throw that in your code with our SDKs, and you can feel comfortable that your tests are exercising that logic. If it doesn't ever get hit, there's either a bug or you're not testing it well enough, and that's a great way to signal that. And the beauty is, if you use our SDKs, it actually gives it more guidance. It knows you care about that area. It's sort of like coverage plus. And it's just a great way to get more tests basically for free. But those are simple, very similar to simple assertions, but where it gets really cool is with our temporal reasoning. So we know the exact execution order of everything that happened on your system across all of your containers. So we can insert very interesting properties. A very common example is a lot of customers, when they have a lot of faults going on, they just want their containers to crash. Like they just don't want to lose data by accident. They just know they're not going to recover, so they want to crash. But they want to assert that they're only crashing in those exact situations. So you can write a property, this is sort of pseudocode, but close enough to what it would look like, and where you only are crashing when the specific faults you care about are happening. And we are asserting this across all possible executions that our fuzzer has seen. Across every random permutation of faults and everything. Anything that's happening in your system, we have a full observability kind of style there too.
This is a lot more powerful than it looks at first glance. We have one of the first questions a lot of customers ask is like, oh, you're hitting us too hard. Can we dial this back? We weren't designed to support this. But of course, having good crash paths is really important. You don't want to, it's okay if you can't run without any network access indefinitely, right? Like you're supposed to be on the internet. But it's not okay if having your network cut off makes you expose data that you were supposed to be keeping secure. You want to be able to test that stuff, but you can't have the crashes polluting your results. So being able to filter this out lets us do harder and more interesting tests for the bad cases that still happen.
Right. And what's beautiful is that we can run this cold on existing data from old runs. We can treat Antithesis like an observability platform just for your tests. And the coolest piece is, so our properties help find some bugs, but when someone tells you a bug report, what's the first thing you probably ask for? You're like, oh, can I get some logs? Can you tell me what version you're running on? Oh, if you're really good, can you get me a service health of all of your systems? And we can get all that for you basically for free, again, because of determinism. But we get even more than that. Say, for example, you want a core dump. A core dump is usually a really destructive process. You have to kill the process to get all that information out of it. So if you knew a bug was going to happen, how would you know to get a core dump before it? But because we can reproduce any event we've seen, we can get you a core dump 10 seconds before, 5 seconds before, or even 5 seconds after. At any point you want, we can make it happen because we can always reproduce that exact same bug. We could even run arbitrary scripts, like you have a Python script to check the health status of everything. We could run that. And sometimes a bug requires a lot of things to happen. Maybe it shows up at time 100, but really a fault happened at time 10, maybe another one happened at 30 seconds, and maybe another one at 60 seconds. We can just rewind, go back, and explore along that whole branch to see the probability over time. Each time we explore, we're doing slightly different things So we can somewhat calculate how likely this bug is. And this is all because of determinism. We can poke and prod at the system, break things, try new things, do whatever we want, because we can always reproduce that same bug and never worry we're not going to get it back. So we've built all these crazy features that we wanted, but how did we know that we actually needed it?
Right. So it's one thing to say, oh man, this is all super cool. It's another thing to go to the VP of engineering and say, can we stop and make our stuff work with Antithesis now, please? So we actually decided to be objective about it, and for a couple of months, we kept a running list of all the bugs we found and that snuck through our tests or that we thought were caught by the wrong tests, and started, as we fixed them, we asked the question for each one, which of our tests should have caught this? Should it have been, the fuzzer? Should it have been a new property in our end-to-end tests? Was there a way we could have, written our types so the compiler could have caught it? And when we stopped and did the math, something like 40% of our bugs could only have been caught with a full system simulation like the one that we were building for ourselves. So, we had to do it. We pulled the trigger. And we knew up front that it wasn't going to be super easy. And to talk about why, I think it's worth taking it from the other direction and asking, who are our favorite customers? What is the ideal Antithesis customer in 2024?
So an ideal customer has a few properties. First up, they run on containers. Like we said before, you're probably deploying containers anyway, so you can just run it in our, in our platform for free, and we get all the beautiful fault injection properties from that. So they really should be running on a container. Second up is running on Linux. Obviously, Linux is the OS we decided to run on top of the hypervisor, and we'd love to support more eventually, but most people run Linux for their servers, so it's usually not a big deal. And thirdly is running on bad networks. And what I mean by that is being fault tolerant. Fault tolerance testing is just in our blood. Our founders were at Foundation DB where they popularized fault tolerance deterministic simulation testing. So just what was our natural fit to do? We could do more than that, but fault tolerance testing is really our bread and butter. And then finally is running offline. Like I hinted at before, we just can't let you talk to the outside world and make our determinism still work. So anything that you need your system to talk to, you need to provide to us. Because if we don't, we'll never be able to fully reproduce every bug we find.
So how close were we to being the ideal customer when we decided to test ourselves? Anybody remember the name of the talk? You might be able to guess. So let's start with the easy one. Runs on containers. I think a few people in this room probably recognize that logo. Because Antithesis builds so many different strange things, we've fallen in with a technology called Nix. We absolutely love it. It lets us deploy all of our dependencies consistently without containers. It's fantastic, but it's just one more way that we weren't the customer that we were expecting. So good news is Nix makes it relatively easy to put containers together, and this is something that we've run into with some of our customers that, for whatever reason, have a different deployment scheme. You can put a Docker file at the end of your CI. You can use Nix Docker tools. There are ways in every ecosystem to bang this out. It's not a huge deal, but it was a thing in our way. But you'd think NixOS would be enough esoteric operating systems for one startup, but we decided very early when we were building out the hypervisor to fork an open source hypervisor, and that was for FreeBSD, and so our hypervisor only runs on FreeBSD. So this most basic thing that all of our customers totally shrug off looked like it was in our way, right? This is a super important part of our stack. It's something we care a lot about. And we just don't have a way to test it. We're working on it. We've got some exciting ideas about nested virtualization. Someday we'll run, the hypervisor on FreeBSD in Linux and the hypervisor on FreeBSD. But that's not working quite yet. And so in the meantime, we had to think about our system, right? Because we want to test as many things as possible. But we wanted to make sure we weren't making the perfect the enemy of the good. So when we look at our actual architecture, the hypervisor is really core to our offering, but it's not very central to the graph of our system. The only thing it talks to is the fuzzer that's driving the software exploration. So if we swapped it out with another toy emulator that had the same API, we could still exercise all of the rest of our system. We could still see the faults where things meet. We could still run things together. And we've just got to depend on all of our other testing to take care of the hypervisor in the meantime. And this is true for everybody, right? Like, don't let the fact that one thing is really hard to test keep you from getting good tests around as much as possible, right? Bugs hide anywhere you let them. And so it's worth trying to push them out wherever you can, even when there's something even better on the horizon. Runs on bad networks. So the core Antithesis customer is, like an event system or a distributed database. They're somebody who cares a lot about uptime. They're really worried about the sorts of faults that can bring their system down. We're a testing service. We do long-running batch jobs for the most part. Our fastest tests for customers take something like an hour. If our entire system goes down and it's the worst case red alert, Will has to come in on the weekend to turn something back on, our customers perceive it more as like a delay than an outage. Just network fault tolerance is a thing that we care about in the long term and increasingly in the medium term. But when we were starting to test ourselves, it just wasn't at the top of our priority list. On the other hand, we felt a lot like the dog in the meme here, where there were a lot of fault tolerance properties that we were worried about, right? We were worried, what happens if the messages that we're sending to ourselves come in an order that they could totally, but that they don't usually? What about the sort of surprising edge cases where all of our pieces meet? We still wanted to test all of that stuff, so we still wanted our fault injector. But when we first turned it on and used the normal level of faults that we throw at all of our customers, everything went down immediately, and we couldn't find anything else. So what we decided we had to do here is actually strengthen our invariance, right? We went back to the same trick we pulled when we made the fuzzer deterministic, and we said, no, okay, now it's time for us to worry about recovery, to worry about availability, to worry about, actually living on a network where things go wrong. Because the crashes that we sort of thought were okay, these are rare events, they're long tail, we're hiding other bugs that even by our standards then were real that we cared about. We needed to make our system stronger in order to make the testing easier, in order to find the bugs we were most afraid of. And finally, runs offline. So we're a SaaS company. We live in the cloud. We love our cloud providers for the most part. We depend, we try not to build against super crazy proprietary stuff, but we're not going to turn down a good API if one's available, and we're solving enough hard problems. So when we built out our system, we've got calls to our cloud provider SDKs all over the place. And unlike our hypervisor, which is sort of sitting in a corner, this stuff is all throughout the way that our systems interact, right? It's our network, it's our job provisioning, it's our database. So, thankfully the AWS side of this was super easy, and that's where we have most of our stuff. There's a great open source mock that was actually so easy to integrate that we're getting ready to offer that as a general purpose feature to customers where they can have a very low touch Amazon mock hanging out in our environment. The Google side was not that easy. So GCP has some first-party mocks, but not for the service that we care most about, which is BigQuery. There is an absolute hero who has put together an open-source BigQuery mock. But we're sort of unusual users of a database, right? We're trying to keep this, we would like to stream in a multiversal tree of events and then do arbitrary folds along selected branches. We want to ask what are all the ancestors of something? BigQuery has no idea there's even a tree in there. So we are using every feature that they are offering us, and we have turned out to be excellent testers of this BigQuery mock. We have found every single place that this thing has deviated from the spec, I'm pretty sure. We've put in some PRs, we patched some stuff. We're intense, but we got it working. it felt a little silly sometimes to spend days trying to get a mock working for a service that isn't the service we're trying to test. But it was so central to what we were doing that stubbing it out or having an alternate offline mode would have meant leaving out a lot of our most sensitive code, a lot of the stuff that is most likely to have exactly these race conditions and fault tolerance bugs that we're so good at finding out. But we got through it. We did it. We had ourselves inside Antithesis. We turned it on. We got a report, and we moved into a new world of testing.
And this world is giving us a lot of confidence. It's giving us confidence to fix these Heisenberg bugs, these things that we're seeing in production that we could never reproduce locally. And then it's letting us build more cross-cutting features, so features that are touching our entire code base that were just scared us to merge without any great testing framework. And it's making us more proactive to do code maintenance that we've been dreading too much. Stuff that just we were always worried to do because we were never worried that we were tested strong enough. But first up, we kind of want to go into an error case that we found first.
Yeah, so, this is a bug that was, hanging out in our stack for several months. It's a Rust panic, but it was a panic in a service that was set to restart itself. It seemed like it mostly happened when, other things weren't paying attention. It wasn't the cause of any outages. The main way we knew it was even in there was if something else went wrong, we would comb through the logs and be like, oh, that came up 3 days ago. Add another tally to the mysterious Rust panic chart. We'll get to it someday, right? But there are a million things to do, and if we've got a bug hanging out that's totally asymptomatic and we have no idea what's causing it, they're just it didn't feel like the thing to prioritize. We just sort of, maybe it'll go away on its own. Who knows?
But then we found it. On literally the first night of us running Antithesis, we saw this error where of no unexpected crashes. And this is great because this is an invariant that I didn't even know this error was happening in production. I didn't know Brian was dealing with it all the time. Antithesis just told me a container crashed. So when I go and look into the logs, and don't really worry if you can read it, it's not a big deal. But at the end, we see that same exact Rust panic. But much earlier, we see our fuzzer has its own assertion failure, and which caused that to die. So that got us to think, hey, is this always the case? Is it the fuzzer that's really the root cause of this bug? And instead of standing around all day pontificating and going through logs, we can just use all of the great features that we've built. So we made a temporal property that just says, hey, look for that Rust panic, and then anytime you see, and then also look for the fuzzer assertion failure, and then make sure that every time the proxy error is seen, a fuzzer error has to happen before it, every time. And like I said before, we can just run this on the data from the night before, and in seconds, that was true. Every time we see that error, it's because of the fuzzer. So really 2 bugs were going on. The fuzzer had some assertion failure because whatever reason, it wasn't really a big deal, and which led to this proxy error. And that's why it was so hard to trace down in production, because every time we saw that error, we fixed the root cause in the fuzzer or somewhere else. And that error went away for a while, only to show back up a few months later. And what's great is that since we have the full context of what is going on now, we knew exactly the dependency that was causing us pain. We were able to fix it, and this was a few months ago, and since then, we've never seen the error again. So Antithesis is giving us the confidence that anytime something's going to go wrong, it's going to catch it for us, which is making us take on bigger things.
And when you actually start seeing that, it really does sink into your mindset, right? Again, I'm sort of a little given to neuroticism around introducing bugs to our code, and the feeling of comfort of knowing that our tests are actually catching stuff changes the set of things it feels like we can do, right? So somebody had a great idea to overhaul the way that we internally package and deploy all of our stuff. It was going to be awesome. It was going to, utilize our boxes better. It was going to be faster to deploy. It was going to be harder to get mismatched versions set out for. Everything about it was going to be cool. It was also going to touch all of our code. It was, services that were, basically legacy code at this point, where all of the bugs had been found the hard way and they just didn't have any more because we'd filed them all off after years of bug reports. Now we were going to have to go change those again and reopen Pandora's box. That sounds like the sort of thing that could be a disaster project if you don't have good testing. But at this point, we finally did. And so we went off, and it was super cool to be like, yeah, because, every once in a while, I'm the sort of guy who will make a subtle mistake in a state machine that will ruin my life in 6 months. And being able to see that the next morning when I actually know what it is that I was messing with and I can just fix it was so cool. We had the real thing, and it really started to sink in for me when we landed this project, and all of those subtle bugs that I was afraid would be hounding me for months just weren't there. We'd caught them. So anybody here ever done a small project before? The sort of thing where when you look at the pull request, it's only a handful of lines of code, but they're here, there, and everywhere. They're across API boundaries. They're, the sorts of things that are like, you're changing an API, or you're fixing the way your build works, or you're upgrading some sensitive dependencies. They seem like they should be easy, but how do you know you got it right? Right? You can smoke test it, you can turn the thing on, you can see if it still behaves, but I hate projects like that. I hate the existence of, it seems like it should be done, but now there's just a new source of arcane bugs from who knows where in our stack. But imagine a hypothetical coworker. Imagine a hypothetical engineer who is hypersensitive to the risk of leaving these small projects undone. Somebody who really sees the looming threat of letting our dependencies go out of date, or who is afraid to see our engineers get used to APIs that are bad that we want to replace. Somebody who knows how easy it would be to just bang it out and wants to do it, and who's good enough at writing code that when he does it, it always looks like it works. Imagine further that this hypothetical engineer is your CEO, and that as soon as he has this code looking like it's worked, he's whisked off for 2 weeks of meeting with customers and investors and can't actually see it over the line. Not that this has ever happened to me. So the way that I related to these projects before and after we had our antithesis testing was night and day. I was definitely the guy that was like, please, Will, can you just wait 2 weeks and merge this when I have more time for things to be on fire? And it's so nice to be able to have him say, hey, I ran our antithesis tests on it. They passed. It's probably good. And to believe him and to then have it be true. It's not just that I am, less angry at somebody who is otherwise, a great coworker and a friend. It's that, I actually want to do this stuff, right? Now I want to do small projects. Now I want to be the guy who people are like, thank you, you made this, part of my workflow 25% faster doing this thing that you used to be terrified of. It's awesome. It really changes the way that I relate to our code base and what we can do. But so, we've talked about big-ish projects, we've talked about small projects. What about absolutely monstrous projects? What about, the actual crazy stuff? Antithesis has always been on the ambitious side, right? We set out to solve software testing. We've got a little bit of crazy. But, we also know enough to realize which things are scary. Our founders come from FoundationDB, and if there's one thing that working at FoundationDB taught them, it was that building a database is really, really hard. So, as much as we have over the years been frustrated with the limitations of the databases that we've been working with, we've known better than to roll our own. Believing that we can really do it has changed the sets of things that we can do. And we have so many cool ideas for what it would look like if we had a database that really understood our model. We could be faster, we could find new things, it could be awesome. And now we really think we're going to be able to pull it off. We're not going to be selling that to you guys directly. You don't have to worry about it that much. But it's going to enable some awesome features. And we were able to drop it into our antithesis tests in 20 minutes. And it's already helping us work through the first rounds of bugs in the first prototypes of it. It's going to be super cool. And that's our talk. Thank you, everybody. Yeah.